We've been considering situations where if you start off with a sketch of a function, you don't need to know what the actual function is, you just need to know what the sketch looks like. And then if you make some algebraic change to the equation, we've worked out how to draw the new function. Examples we've looked at are where the transformations are translations and stretches. We're now going to look at a third situation. If we know what the graph of y equals f of x looks like, then what would the graph of y equals the negative of f of x look like? So starting with our standard example, let's begin by considering a point right on the edge of the curve, the point with coordinates -4, 5. This means that for an x of -4, f of -4 is 5. We are now trying to draw the curve y is the negative of f of x. The negative of f of x means negative of 5, -5. So on our new curve, we would plot a y value of -5 to go with this x value of -4. That means we would be plotting this point here. And it's therefore easy to see that for a few other points that we could choose, we will always be plotting a y coordinate on our new curve, which is the negative of the y coordinate on our original curve. It's not too difficult to see what happens when we connect all these points together. Let's just get rid of the coordinates, make it a bit easier to see. And so the curve that joins these points looks like this. Here is a graph of y is the negative of f of x. It's not difficult to see how we've got our new curve from our original curve. It's been reflected in the x-axis. So therefore we have a general rule that to go from y is f of x to y is the negative of f of x, what we have is a reflection in the x-axis. However, it is more useful, instead of saying that we have gone from y is f of x to y is the negative of f of x, to rewrite the final form in the form negative y is f of x. Now it is easier to see what the actual change that has taken place is. We have replaced the y in the original equation by a negative y. More formally, we have the first of our reflection rules to go with our translation and stretch rules. If we replace y with negative y, then the transformation that goes with that is a reflection in the x-axis. A similar question would be this. If we know what the graph of y equals f of x looks like, then what would the graph of y equals f of negative x look like? Well, going back to our standard example, so let us see if we can work out which point we would have to plot to correspond to our original point of -4, 5. In other words, we know that f of -4 is 5. Well, that means that on our new curve, y equals the f of negative x. Now, if x is -4, then the negative of x, the negative of -4, is +4. That means that we need to plot the y value that goes with this point, the 5, not above -4, but above +4. We should be plotting this point here. Similarly, if f of -3 is 2, then we need to be plotting this y value of 2 not above -3, but above +3. And we can continue this pattern through our other values of x. Removing our coordinates to make it easier to see, it's now not difficult to understand what will happen when we put a curve through all of these points. The graph that goes with y is f of negative x is the same as the graph of y equals f of x, but it has been reflected this time in the y-axis. So what we have is a reflection in the y-axis. And if we go back to think about it algebraically, it's already in a quite useful form. We can see that if we go from y is equal to f of x to y is equal to f of negative x, then what we've changed is every time there's an x on this side, it has been changed to negative x on this side. More formally, we have this second reflection rule. If we replace x with negative x, we have a reflection in the y-axis. And in a similar way to what we saw with our translation rules and our stretch rules, these two reflection rules are really just one rule. There's a lot of symmetry going on here. If we replace x or y with negative x or negative y, then we have a reflection in the y or x axis, respectively. Let's illustrate all of this with an example which may be a little familiar by now to you if you have seen the translation and stretch videos. The diagram shows a sketch of part of the curve with equation y equals f of x. The curve intersects the x-axis at A and C and has a minimum point at B. On the same diagram, sketch the curve with equations y equals the negative of f of x, y equals f of negative x, and y equals f of negative 2x. You should show the coordinates of the images of the points A, B and C on your sketches. The curve isn't that easy to see on that diagram, so here's a close-up of it. We can see that the intersection points A and C are negative 6, 0 and 9, 0, and the point B, the minimum, is negative 1, negative 6. Well, before we have a look at what those transformations do to the curve, let's see if we can work it out using our rules. For part A, we have to work out how to go from the curve with equation y is equal to f of x to the curve with equation y is equal to the negative of f of x. And it would be better for us to write this second equation as negative y is f of x, which we can do by multiplying through by minus 1. So we can see that the change that has been made is that y has been replaced with negative y, which our rules tell us should be a reflection in the x-axis. So looking now at the transformed version of that curve, it is indeed the same curve reflected in the x-axis. And if we look at where the points A and C have ended up, well, they are on the x-axis, so both of those will have images which are in the same places. But the point B, which was originally at negative 1, negative 6, has an image at the point negative 1, 6. Now let us see what we think should happen in part B, because in part B we have to work out how to go from the original curve y is equal to f of x to the new curve y is equal to f of negative x. Well, we can see that x has been replaced in the original equation by negative x, so our rules tell us that what we should see is a reflection in the y-axis. And this time then, when we see the new curve, y is equal to f of negative x, it is a reflection of the curve we started off with in the y-axis. The point A, which was at negative 6, 0, is now at 6, 0. The point C, which was at 9, 0, has now been reflected to negative 9, 0. And the point B, at negative 1, negative 6, has been reflected, so it is now at 1, negative 6. Part C offers an extra challenge, because in Part C we have to work out how to go from the curve y is equal to f of x and end up with the curve y is equal to f of negative 2x. Now, although it is possible to do this in one go, I would suggest we break it down into two stages. I would first off say, how do we get from y is equal to f of x to y is equal to f of negative x? Well, just as in our previous example, that means we have replaced x by negative x, so that means that we would expect to have a reflection in the y-axis. But we're not at our final destination. Once we've got to this point, we then want to turn this into y is equal to f of negative 2x. Now what we've done here is we have replaced x by 2x. because we already have a negative x there. If you change this x into a 2x, we'll go from a negative x to a negative 2x. And 2x is the same thing as x divided by a half. So what we would expect to have here is a stretch parallel to the x-axis of scale factor a half. So the transformation of our original curve that we would expect to see is one which follows both of these two transformations, first reflected in the y-axis and then stretched parallel to the x-axis in scale factor half. If we were to do those two transformations one after the other, we would end up with this curve. You can see it has been reflected in the y-axis, and it has also been stretched with a scale factor of a half parallel to the x-axis, so everything is now twice as close to the y-axis as it was originally. We can also see the image of the point A, which used to be negative 6, 0. When that was reflected in the y-axis, it would become positive 6, 0, and then it gets stretched to become 3, 0. Similarly, C, which started at 9, 0, is now negative 4.50. B, which started at negative 1, negative 6, is now positive a half, negative 6. Now I did say there was an alternative way of looking at this. We could say instead that we were going from our original curve, our y equals f of x, and turning that into y is f of negative 2x, which we might realize we could rewrite the destination as f of x divided by negative a half, which means that we could just follow one of our stretch rules, and we could say that the transformation is a stretch, it is parallel to the x-axis, and it is of scale factor negative a half. And looking again at our final curve, that sort of makes sense. What would it mean to have a negative scale factor? It would mean that not only do things move around according to the size of the scale factor, the half in this case, meaning that everything is now half the distance it was from the y-axis, but the negative involves the reflection. Things have not only got closer to the axis, they've flipped in it and come out the other side. Now this is a perfectly valid way to describe the transformation, but I would claim it's much clearer to break things down in this two-step way and describe it as a reflection followed by a stretch. However, as a final comment, it's worth going back to our comprehensive list now of transformations and realizing that our stretch transformations are valid not just for k being any value greater than 0, which we've considered before, but for any non-zero value at all.